Okay, so students, today we will discuss on a very interesting topic in optics, which has got so many applications in today's world, and that is polarization of light. So before I discuss on polarization, let us very quickly look into the electromagnetic. What are electromagnetic waves? Because light is an electromagnetic wave, we all know. So you see, this is the nice visual I can draw on the plane of this board, where you can see electromagnetic wave means electric and magnetic field oscillates as the light propagates. So you see the red curve is showing the oscillations of the electric field, and magnetic field is shown by the blue curve, right? And then you see that these electric field oscillations and magnetic field oscillations are perpendicular to each other. So this is how the electromagnetic wave is there, and electromagnetic wave, light is nothing but the electromagnetic wave. In optics, except for very special cases like Faraday rotation, we don't talk about magnetic field. So that is why in optics, the light is shown only by the electric vector. So this wave represents a light wave, oscillation of the electric vector. So light is shown by oscillating electric vector. Of course, there is always a magnetic vector which is oscillating in a perpendicular plane. That is always there. So if I am asked to show the oscillations of the electric vector in a pictorial manner, then this is the way I can show it. Fine. So this shows that if the light is going inside this plane of the board, then electric vector is oscillating like this. Fine. This is how I can show. So this is about the schematic of an electromagnetic wave or an optical wave. So before, in fact, we come to the point polarization, let us first try to understand what is an unpolarized light. So for example, the light normally which you see around, that is unpolarized light. And unpolarized light means what? If light is coming towards you, then the electric vectors, you will see the waves will be having electric vectors oscillating in all possible planes. So if the light is coming towards you, and if the light is unpolarized, then the wave is, the electric vector oscillations are like this also. Some electric vectors are oscillating like this, some are oscillating like this, and so on. So they are oscillating in all possible planes. Now, you know, in physics, we can resolve any vector into two perpendicular vectors. So if I keep on doing with all these vectors, and I have their resolutions in two perpendicular directions, then I will get a scenario like this. So unpolarized light can be represented by this also. So this is what is now we say that unpolarized light, and this is also the unpolarized light. If by some trick I can eliminate one of the polarizations, one of the electric vectors, fine. So if I eliminate this, then I will be left with this only. So which means what? In this light, all waves will be having electric vectors like this. So this light will be called as the plane polarized light. So plane polarized light means what? In plane polarized light, all the electric vectors, they oscillate in a single plane or in a single direction. Is it fine? So if I am having light in which all vectors are oscillating either like this, so it will be plane polarized light. If all are like this, again it will be a plane polarized light. If like this, or all are like this or like this, the light will be plane polarized light. So I hope you understand what is meant by plane polarized light. Fine. So this is what is called polarization of light, and in polarization of light we have just talked about the plane polarized light. Is it fine? Now there are different type. Only plane polarized light is not the everything. We have other kind of polarized light also. So what are different types? We have plane polarized light, we can have circularly polarized light and elliptically polarized light. So, but then in understanding these two, we also must understand what is unpolarized light and what is partially polarized light. So this we will see very quickly in due course. Now how to get plane polarized light, how to obtain, because normally this light, natural light which we have is not a plane polarized light. So how to get plane polarized light? So this is the first way. You know, if you incident unpolarized light in a dielectric interface with an angle equal to Brewster's angle, then the reflected light is plane polarized. Fine. So this is one way of obtaining plane polarized light. What is the way? Just have the reflection at dielectric interface with Brewster's angle, with incident at the Brewster's angle. So this light will be plane polarized light. Some of the light will get transmitted and that will be partially polarized light, but the reflected light will be plane polarized light. So this is one way. Another way is this: by having doubly refracting crystals. You have, in previous classes you have understood what are doubly refracting crystal. So there are doubly refracting crystal. If you incident unpolarized light, if you pass unpolarized light through them, then you will get that light splitted into two components: extraordinary light and ordinary light. And if you examine these two split lights, then you will see that one is plane polarized in a certain plane and other is polarized in the perpendicular plane with respect to the previous one. Fine. So these are mutually perpendicular. These two, ordinary and extraordinary, they are polarized in a mutually perpendicular planes. So this is the way you can have the light, polarized light from the unpolarized light. This is also one way of having polarization. In fact, scattering causes polarization. So if you see distant hills or distant scenario, then you see that scenario is very hazy. Right? So that haziness is because of the light within the medium is getting scattered. Fine. So information which is coming, the optical information which is coming from the distant scenario gets overlapped by the scattered light. But then this scattered light is partially polarized. Fine. So this, but the light information coming from the distant scenario is not polarized. That is unpolarized. And this light, the scattered light, which is making that scenario hazy, is polarized, is partially polarized. So this is also, so scattering also causes polarization. And then lastly, the polarizing films. So by having polarizing films, we can have polarization by transmission. So we have these polarizing films which have got certain pass axis. So if you incident unpolarized light, if you pass unpolarized light through these films, then one component will get eliminated. So you will be, after transmission, what you will get? You will get plane polarized light. So these are polarizing films. I have those polarizing films. I will just show those to you. So before go to this, before I discuss this, I will just show the polarizing films to you. Can you see? Can you see this? Can you see this? Now can you see the change? Is it fine? So these are polarizing films. These are polarizing sheets, polymer sheets, which I have removed from the calculator screens. So this is from the calculator screen. This is again from the calculator screen. So this tells me that these calculator screens, they use polarization of light. Fine. So in fact, soon you will realize that the entire display technology is revolutionized by this phenomenon of polarization. You will soon realize this. So what is happening over here? This is a polarizer, and when this unpolarized light, if I do like this, nothing happens. But if I put it like this and put another and do it like this, now you see the intensity is going from maximum to 0. 0 means black means 0. Fine. And then from black to, that is 0 to maximum. So what is happening? The unpolarized light, when passes through it, suppose for example this has got pass axis like this, then the unpolarized light, after passing through this, all the light will be having this electric vector oriented like this. Now if I keep this polarizer with pass axis aligned to this, like this, now pass axes are aligned. So what is happening? This polarization light and pass axis of this matches and whole of the light gets through. Fine. But then if I put them cross matched, then this will make the light polarized like this. But then in front of this, if I put this polarizer with vertical pass axis, then it will block entire of this light, and what I will see black. Fine. So this is the, now it is going from 0 to maximum and maximum to 0. So when you have the pass axis having angle equal to 0, then whole of the light is passing through, and when it is 90 degree, nothing is getting through. So in between this, how the intensity changes, that is given by Moller's law. Moller's law tells this only. Fine. So this is Moller's law. This is one polarizing sheet. So unpolarized light is getting through it, but that when it gets through it, you see it becomes polarized. And when you rotate another polarizer in front of it, then depending on the theta in between these two pass axes, the amount of light will get through and it will follow this expression. Is it clear? This is Moller's law. Fine. This is Moller's law. Now I will tell you how the display technology is revolutionized because of our understanding of polarization. You just see. Can you see?
Yes, sir.
This means that this is also polarized. So this screen is also using polarization phenomena. Your all these cell phone screens, if those are LCD screens, then those are using like this polarization phenomena. Fine. So this has revolutionized our display technology. So this is but then all this is plain polarization. Now I am talking about application. So one application you just have seen. The application that display technology is revolutionized by the polarization only. Fine. I just wanted to show you one more interesting thing, which is not related to, which is not directly related to our this lecture. But by the way, I am having this LCD screen with me. So this in fact, this screen is having liquid crystals sandwiched between two glass plates. Fine. Now you see, and then there is a polarizer. So I will show you. Can you see what is happening? It is going from 0 to maximum. Fine. But now you see what interesting thing will happen if I do it like this. Can you see?
Yes.
Fine. So this is polarization dispersion. This is not today's topic. But then how interesting optics is, see. If I do it like this, it is just black and white. But when I do it like this, it is colorful. Fine. So someday I will discuss this phenomena also. But then, okay. So this is, in fact, this is so interesting. Now let us talk about applications. So this is one of the very interesting application, and that is polarization photography. You must have seen the professionals, they use cameras, and then nowadays those cameras are essentially, they have polarizers. Fine. So what these polarizers do with this photography, you just see. This is a scenario which has been photographed without a polarizer. Now if I use the polarizer in front of it, and then the polarizer is properly adjusted, the pass axis is properly adjusted, you see the effect. Right? What is happening over here? The scattered component is eliminated. So scattering is noise. Fine. Scattering is basically, it is creating noise in the image. So you eliminate noise without affecting the optical information. So optical information reaches to you without noise. So you eliminate this thing. Fine. This one more, photograph is there, which has been taken without using polarizer, and this is with polarizer. You see the color contrast and the and everything. Fine. So quality is enhanced like anything. This is one photograph. You see there is a frog, which only you can see the head of the frog, which is coming out of the surface of water. Why? Because the visual information which is coming from the inside of the pond is getting overwhelmed by the surface reflection. But just I showed that reflection causes polarization. So I understand at Brewster's angle, it is perfect polarization, but on other angles, which is not Brewster angle, it is partial polarization. Fine. So we can eliminate this. We can eliminate this noise, and we can have such a nice picture. Now we can see surface reflection is completely eliminated, and you can see the inside of the pond very clearly. Isn't it very interesting? So polarization, this classroom lecture, in fact, leads to all these very interesting applications. This is one more application. You must have seen 3D movies. All of you must. And then you notice that in 3D movie, they gave you goggles. Those goggles are basically polarizers. So what is done in this 3D movie? They project. In fact, why I am observing you in 3 dimensions, why I am having the sense of depth when I look at you, because I am having 2 eyes. Okay, na? So what is happening when I look at you from this eye, my view angle is slightly this. And when I look at from this eye, my view angle is slightly this. So there is a parallax between these 2 scenarios. 2 eyes, they are receiving the same scenario with slightly 2 different perception. That results in a parallax. Fine. So when these 2 images simultaneously go into your brain, then brain processes this parallax and extracts the information of depth. समझ में आया? इस तरह से होता है. In nature we see depth because of this only. So later on I will just tell you, I will answer to each of your query, because of course you will be asking me that when I close one eye then still I see the depth. Then how come I do that? So that answers I will give you later on. But then for the time being you just keep in mind that this sense of depth is only because of we have got these two eyes. Major, I mean the major cause is this only, fine. It is due to our two eyes. So what is done in 3D movie, they project, they first of all they record the scenario with two perceptions. So there will be two cameras, those will be filming one scenario simultaneously or one happening simultaneously. So one will record from this perception and other will record from this perception. Now these two scenarios will simultaneously be projected on the screen. Fine? But then while projecting those, in front of one, it will be this polarization will be kept. So all the light passing through one projector will be this polarized, and all the light passing through another projector will be this polarized. So these scenarios will be projected. If you remove your goggles, you will see very hazy picture. Hazy picture. In fact, two pictures are being overlapped. But then when you wear goggles, then only one scenario will go into your one eye. Fine? So your one eye will get this perception and this eye will get this perception. So you will start observing everything in 3 dimension. So this is what is done. This is what is explained over here. Fine. So now next time when you go to a cinema hall for a 3D movie, then you do all kind of experimentation. You remove it, you do it like this, ऐसे करके देखिए. Then you will realize, fine, what I am saying. The moment you just close one of your eye goggle, उसमें in 3D movie hall, you will see everything two-dimensional. Your ordinary movie, fine. And then if you remove it, then it will be hazy scenario, two in fact scenario overlapping. So now before we conclude, very quickly I will tell you the meaning of elliptically and circularly polarized light. So for that I will use this bob which is oscillating in simple harmonic motion. So this is a bob which is oscillating. So these are two extreme positions of oscillations and this is the mean position. So at mean position the phase is written as 0 and path is also written as 0, corresponding path is 0. When it reaches to this extreme, then of course the phase is pi by 2 and corresponding path is lambda by 4. When it comes back to this position, then you know phase is pi and corresponding path is lambda by 2. When this goes to this extreme, phase is 3 pi by 2 and corresponding path is 3 lambda by 4. And when it comes back to this position, completing its one cycle. So this is one cycle. So the phase becomes 2 pi and corresponding path is lambda. So so this is one cycle and 2 pi. Fine. In angular term it is 2 pi and in length term it is one wavelength. Fine. So this is how we have it. Now you just imagine that this bob is oscillating like this and I give a kick to this bob from this side. When it reaches to its max extreme, what will happen? What will happen to the bob? You can, in fact, you can do this experimentation. This bob is oscillating and at extreme you give a kick like this, so it will start circulating. Fine. So same thing you can do in optics with electric vectors. So now if you have electric vector means oscillations, simple harmonic oscillations. So simple harmonic oscillations of electric vector. So if you have one electric vector oscillating one wave like this, other wave like this, because this oscillation is in this direction and I gave a kick into perpendicular direction. Fine. So I put these two like this and create a path difference in between these two equal to lambda by 4. Then what I will be having? I will be having the electric vector now not oscillating but circulating with the propagation. So this is called electric vector, I mean circularly polarized line. Now if I keep this amplitude larger and this amplitude smaller, then it will be oscillating like this. So that will be your elliptically polarized line. If I keep this amplitude very large and this amplitude very small, then it will be elliptically, again elliptically with this polarization. So how much time I have left? How much time I am having? In fact, now we can do very quick, very simple, in fact, this mathematical treatment. I write one wave as A sin omega t plus delta and other as y is equal to B sin omega t. So omega means they have same wavelength, fine, and x and y means perpendicular. Fine. Delta, because I want to make them one going ahead of the other. So phase I want to change, so I write here phase part. If phase part is 0, which means that both are going along, fine, with 0 phase. So from here quickly I can write y by b is equal to sin omega t. So cos omega t is equal to 1 minus sin, fine, this is. And then x by a I can write this, looking at this, fine. So x by a, by using this over here, I can write it like this, fine. Isn't it very simple? So further simplification results, you can just make manipulations, bring that term over here and simplify. So you get this. This is the general equation of an ellipse. So when you mix two perpendicular polarizations, so in general that will be an ellipse. Resultant will be an ellipse. But then you just consider some special cases. If you put delta equal to 0, साथ में ये दोनों, then y is equal to bx by a. So this is nothing but the equation of a straight line. So if you have these two polarizations superimposed with 0 path difference or 0 phase difference, then the resultant light will be plane polarized line. ऐसे होगा. But then it will be inclined. This it will, and the inclination will be given by this b by a. ठीक है ना? If you have path difference equal to this much, so lambda by 2 is also there. Put n equal to 0, so that will result in pi by 2. Pi by 2 and so on. For all these values of delta, you just have that general equation, you will get this. So this is again the equation of an ellipse. But if a is equal to b, then that makes this an equation of a circle. ठीक है, तो ऐसे ही होता है. अब आप देख लीजिए कि जैसे पेंडुलम हो रहा है, पेंडुलम ऐसे ऑसिलेट हो रहा है और आप 0 पे उसको ऐसे किक देंगे ना तो वो ऐसे होने लगेगा. 90 पे देंगे तो ऐसे होगा, इधर देंगे तो ऐसे होगा. सो यू कैन make right circularly polarized light, you can make left circularly polarized light, fine. You can change the polarization by giving a kick at the 0 phase, fine, like this. So by having this mechanical analogy, you can play with the optical vectors also, but then you should have the ability to create proper path differences or phase differences between the two superimposing waves. So how do we do that? How do we create desired path differences? That we will discuss in due course. So I stop here only. Fine. You can ask question. Do you have any question? Is it clear to all? Polarization is clear to all? Was it interesting? Very interesting.